Anyway, sorry guys. Gotta love chance. But so beta decay is our second type. Now this one is a little bit more dangerous, but it's like a lot more dangerous. And that has to do with the fact that an electron is shot off. And if you remember, electrons are so small, or beta particles in this case, are so small that they technically don't even have any weight. If you remember when we did our simulator, if you took an electron off that circle, and I'll pull up that simulator in case you remember so you know what it looks like. Remember, it was the p hat. This is probably it. Let me pull it up real quick so you can see what I'm talking about. If you remember when we were doing our atoms here, let's pull up our mass number, tell me how heavy it is. If I add a proton, it goes up one. Add a neutron, it goes up one. Electrons, I could add this whole bucket and you will not see that weight go up because electrons are so small they technically don't even count as having weight. Hold on. Let me go back to here. I'm going here. And that's why this is so dangerous, because these tiny little pieces can shoot through the air and go through basically anything. How does this happen? A neutron decomposes into a proton and an electron. The proton is large and stuck in the nucleus. The small electron is easily given off. Because it's so small, it's really easy to kind of get loose from a very unstable element. These particles are much smaller, they're much lighter. It allows them to travel much more quickly, and protection from beta particles requires a sheet of metal. So if there are beta particles being emitted from something, that's where you might find, like if you get an X-ray. Sorry guys, Chance keeps interrupting this video here. When you get an X-ray at the dentist, you'll wear that it's like a little bib kind of thing that covers your belly and your heart and your intestines and everything. It's covering those vital organs. That actually has little pieces of metal in it to protect you from anything that could be coming off an X-ray. But this is where you're going to need something a little bit thicker than clothing to stop this. They might use things like lead or stainless steel. Now, gamma. These are the very dangerous guys. This type of decay does not even include particles. In this case, the radiation, there's so much instability. There's such a lack of stability, and that, if you remember that nucleus, let's go back here for a second. If I can show whether or not it's stable, if I keep adding these, see how it's shaking? It is shaking so much. It's not even going to break down. It's just going to give away this gigantic wave of energy. So let me move this over for a second because I cannot get to your slides. Here we go. So what's happening in this case, during an episode of gamma radiation, an unstable nucleus sends out an energy wave that moves at the speed of light. So this thing is cruising, this huge amount of energy that will just go through anything that is near it. Now, this is what happened at those very dangerous sites like Chernobyl. Now there's a lot of gamma radiation going on. There's no mass, there's no charge, it's just pure energy, like blind, you can't see it, invisible energy just moving. Gamma rays do not change the mass in any way, just the energy of the nucleus. It does, when gamma radiation is given off, it does slow down the element, how shaky it is. It gets slower and slower each time gamma radiation happens. This is our most dangerous. Gamma rays can accompany both alpha and beta particles. So here's why this is so dangerous. When alpha radiation could happen and gamma will join in. So yeah, your shirt helps you that you're wearing with alpha, but now you also have this big ray of energy coming through you that you can't see. So you're gonna have really thick lead or concrete. Now that if you go to Chernobyl today, the reactor that's still giving off radiation, there's huge walls of concrete. Let's even pull it up. Chernobyl reactor today. If we were to look at pictures of it, see that big thick wall right there? Inside this gigantic dome, that's 3 feet deep of concrete to try to keep that in there. Because this is what it looked like after the explosion. Here's the reactor that broke down. You actually see there's where the explosion was. See how those walls are all broken down? Now, that whole area is protected by, there's a thin layer of lead and then there's concrete to try to stop that spread of gamma radiation. And you really can't. That's the sad part. So This video I'm not going to play. I am going to attach it so you can kind of see, and it shows how it moves through your body. Now, if you notice, alpha radiation is so weak that it doesn't even get through your skin. Like, your skin is a big enough barrier to keep it from getting inside your body, but that doesn't mean it can't. If this is like where skin cancer and things happen, like UV rays give off alpha radiation sometimes, so you get skin cancer or something like that. So it's still not anything to play with. All right. So guys, I hoped it helped to kind of hear me talk about this stuff. If not, if I got annoying, I am not offended if you turned me off and just went through it yourself. All right, guys, hang in there. I miss you. Bye.